Welcome to Training Module 10, where we'll focus on the critical process of testing and commissioning electrical grids, specifically the battery bank and battery charger. This module is designed to equip you with the essential knowledge and skills to ensure these systems operate reliably and efficiently. As we move through, you'll learn the key steps and best practices necessary for successful commissioning. Let's dive into the details and understand how to keep our electrical grid running smoothly. On this slide, we focus on the reference framework for testing and commissioning the electrical grid. These references are essential because they guide the creation of commissioning manuals and test scripts, ensuring everything is done correctly. We rely on well-known standards and organizations such as IEC, which stands for the International Electrotechnical Commission, IEEE, the Institute of Electrical and Electronics Engineers, and ASTM, the American Society for Testing and Materials. Other important bodies include NEMA, the National Electrical Manufacturers Association, ANSI, the American National Standards Institute, and specialized groups like SIGER, ICA, and KEMA, which is an electrical engineering verification body. A key governance rule to remember is that when there are differences between a project specification, manufacturer instructions, and standards, we always apply the most stringent approved requirement. It's also crucial to document the reference used on the test sheet for transparency and traceability, so future reviewers can understand why a particular result was accepted. This helps maintain quality and accountability throughout the commissioning process. Here we have the battery bank and unit testing schematic, which is essential for the testing and commissioning of the electrical grid. This schematic serves as a reference for several critical tests, including measuring the open circuit voltage, checking specific gravity, assessing internal resistance, ensuring charger isolation, and conducting controlled discharge tests. Each of these tests ensures the battery system operates reliably and efficiently before it is fully commissioned. This detailed approach helps us maintain system integrity and performance throughout its life cycle. On this slide, we focus on the comprehensive testing procedure for the battery bank and individual units. The core goal is to verify several critical parameters, including battery cell condition, open circuit voltage, specific gravity, internal resistance, discharge performance, and final recharge, all aligned with the approved schematic connections. We start with a mechanical and visual inspection to ensure everything from the battery rack to electrolyte levels and safety measures are in proper order. Then, safety controls like circuit breaker isolation, tagging, PP, and barricades are implemented before we proceed. It's essential to measure and record the open circuit voltage for each cell and the total bank voltage to establish a baseline. Next, specific gravity readings are taken with a hydrometer, along with ambient conditions, which help assess electrolyte health. After initial charging, these measurements are repeated to spot any weak or abnormal cells, which must be addressed before moving on. We also individually measure the internal resistance of each cell, which offers insight into cell health not visible through voltage or gravity readings alone. Preparing for the discharge test requires confirming that the bank hasn't been recently discharged, measuring float voltage, and disconnecting the charger. The discharge test itself is conducted using an ampere-hour-based rate over 10 hours, maintaining current and logging voltage periodically to evaluate performance. The battery bank is then fully recharged. The acceptance criteria require all visual and electrical parameters to fall within manufacturer and project limits, with no damaged cells, abnormal heating, or unsafe conditions. Finally, comprehensive documentation, including test sheets, calibration certificates, photos, and logs, serve as the test evidence. This whole process concludes with a hold point where client and operational teams witness and confirm the battery bank's readiness before it returns to service. Here we have the battery charger testing schematic, which serves as a crucial reference for several key procedures. This schematic guides us through float and boost charger testing, ensuring the chargers operate correctly in both modes. It also details the proper connection of the DC load bank, which is essential for simulating real operating conditions. Additionally, the schematic includes instructions for measuring ripple voltage, an important indicator of power quality, and calculating charger efficiency. All of these steps are vital for the successful testing and commissioning of the electrical grid, as outlined in Commissioning Manual Number 10-2. Let's walk through the battery charger testing process step by step. First, we begin with a thorough mechanical and visual inspection, ensuring all charger tags, AC input, DC output, MCCB status, ventilation, alarms, and safety signage are in proper condition. Then, we connect the DC load bank to simulate variable loads and verify that the battery isolation and circuit breakers are in the correct test positions. Next, we set the charger to float mode and measure AC input voltages, currents, frequency, as well as DC output voltage and current across various load levels from 0 to full load. It's important to also measure the DC output ripple voltage with the battery disconnected, using AC settings on the meter. We then record the charger's own display readings and compare these with independent meter measurements for accuracy. Using these measurements, we calculate the AC input power, DC output power, and the overall efficiency of the charger, taking into account the power factor. The charger is then set to boost or equalize mode, and selected load steps are repeated, typically at 50% and 100% of rated current. Finally, the charger mode is restored to normal operation. Temporary load connections are removed, and the battery and charger statuses are verified. Throughout the process, all parameters like AC and DC voltages and currents, ripple levels, and efficiency must meet the manufacturer's and project specifications. We also check that the load response is stable without any abnormal alarms or incorrect indications. Documentation includes comprehensive test sheets, readings for each load step, efficiency calculations, HMI screenshots, calibration certificates, and a restoration checklist. At the hold point, the commissioning witness confirms all test results and the successful return of the charger to normal service before moving forward. This thorough testing and verification ensures reliable performance and safety of the battery charger within the electrical grid. Here we have the battery charger functional checks schematic, which is crucial during testing and commissioning of the electrical grid. This schematic serves as a reference for several important functions, including alarms, shutdown procedures, lamp tests, current limits, and the soft start feature. Additionally, it covers optional monitoring devices that help ensure the charger operates reliably. Understanding this schematic is key to performing thorough and effective commissioning, as outlined in Commissioning Manual number 10-3. This battery charger functional checks test script is designed to ensure that every critical aspect of the charger's operation is verified thoroughly. We start by confirming that all prerequisites, safety measures, and permissions are in place for testing simulated alarms and shutdowns. Then, we perform a lamp test to verify that all indicators, LEDs, and HMI messages respond correctly. Next, we check the high and low DC output voltage alarms and shutdown functions, confirming both local and remote indications. We also test the ground monitoring system to detect any positive or negative alarms without causing unsafe conditions. Protective alarms, including AC failure, charger failure, and fuse or MCCB trips, are carefully examined to ensure they function properly. We proceed to test switches, push buttons, timers, as well as current limit and soft start functions, including manual and automatic control modes. Impedance monitors and silicon droppers are verified where installed, recording both normal and abnormal readings. Finally, all temporary links are removed, alarms are reset, and event logs are checked to confirm the charger returns to normal service. The acceptance criteria require that all functions operate as specified, with no active alarms or test links remaining. The result package includes the functional check sheet, alarm and event log screenshots, remote alarm proofs, reset checklists, and a witness sign-off. The process reaches a hold point only after operations confirm the charger has returned to normal mode. All alarms are cleared, the battery is connected properly, and DC supply to critical circuits remains available. This careful process ensures the charger operates reliably and safely within the electrical grid.